Since now we have learned about the complex numbers, our discussions of the zeros of polynomial functions now include complex zeros. Let's first look at two theorems. The fundamental theorem of algebra, which states that for a polynomial function that is not a constant function, in other words, its degree n is bigger than 0, it must have at least one complex zero. Derived from this theorem, we have the linear factorization theorem, which states that for, again, a non-constant polynomial function of degree n, it can be written as the product of precisely n linear factors, which means that for this polynomial function with degree n, it can be written as an, the leading coefficient, multiplied by exactly n linear factors multiplied together. Here, C1, C2, etc., all the way to Cn are all complex zeros of fx, meaning that they could be real numbers, but they could also be imaginary numbers. And by the way, there could be repeated zeros. Now we've learned that this polynomial function of nth degree can be completely factorized into the product of precisely n linear factors. The question is, how do we factorize it? How do we find the zeros for it? If you do have a graphing utility, my favorite method is simply to sketch the graph for this function and look at the x-intercepts on the graph, which correspond to the real zeros of the function. And that can get me started with the factorization. If you don't use a graphing method, then you probably have to use the trial and error method, which simply means that you have to test different numbers out to try for the first zero for this function. One of the tips is the rational zero test, which means that for this polynomial function, if all of its coefficients are integers, positive or negative or 0, and if this function has rational zeros, then the rational zero must have the form of p over q. Here, p is a factor of the constant term a0, and q is a factor of the leading coefficient an. And by the way, as you probably already know, the polynomial function could have irrational zeros and even imaginary zeros. But this only works for rational zeros. For example, let's say we need to completely factorize this third-degree polynomial function. And this function does have all coefficients being integers, therefore we can use the rational zero test, which means that if this function has a rational zero, it must have the form of p over q. Again, p is a factor of the constant term a0. In this case, a0 is 20. And how many factors does 20 have? We have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and then plus or minus 20. So overall, 12 possibilities for the value of p. And q is the factor of the leading coefficient an, in this case 3. Therefore, the possibilities for q only include plus or minus 1 and plus or minus 3. However, the quotient of p over q has all these different combinations. Therefore, all of them could be a zero for this function. And at this point, you simply need to start testing them. The easiest way is to substitute these values using your calculator into this function to see which one of them will make your function goes to 0, because that's the definition of a 0. And fortunately for this example, you don't have to test too many times, because x equals to negative 2 is indeed a 0 for this function. And as soon as we find one 0, we can pause the testing and use the method synthetic division that we learned to start factorize this function. So we draw the symbol for synthetic division, fill in the coefficients of the function, fill in here the 0, and then start the synthetic division procedure. Write down the first coefficient, multiply it by -2, -6, and then we do addition. 11 plus -6 is +5. Multiplication, -10, addition again, 10 times -2, -20, and then addition again. Here, the remainder is 0. That's what we wanted to see. This means that the original function equals to x plus 2, which is the factor corresponds to the first 0, -2, multiplied by a quadratic factor, 3x squared plus 5x plus 10. So what do we do next? Tip 2. Don't forget about the quadratic formula. As soon as you see a quadratic factor, you can always use the quadratic formula to further factorize it. Say for your polynomial function, ax squared plus bx plus c is a quadratic factor. From here, you can always solve for two zeros using the quadratic formula, and these two zeros, x1, x2, correspond to the two factors x minus x1 and x minus x2. So continue with this problem. We do have a quadratic factor here, 3x squared plus 5x plus 10. Therefore, we can use the quadratic formula, substitute in coefficients a, b, c. A is 3, b is 5, and c is 10. And then, in this case, the two zeros are imaginary zeros. But still, they are zeros to this function, and they correspond to the linear factors x minus x1 and x minus x2. And now, this third-degree polynomial function is completely factorized into product of exactly 3 linear factors. Again, the number of linear factors is 3, which corresponds with the degree of this function. And that completes this problem. Let's look at another tip. If a polynomial function has all real numbers being its coefficients, but it does have a complex 0, a plus bi, then the conjugate number a minus bi must also be the 0 for this polynomial function. In other words, for this polynomial function, its complex zeros always show up as conjugate pairs. So these two complex zeros, a plus bi and a minus bi, correspond to two linear factors, x minus a plus bi and x minus a minus bi. And the product of these two linear factors is, we can carry out the calculation, and this becomes x minus a squared plus b squared, which is x squared minus 2ax plus a squared plus b squared. And recognize that this is a quadratic factor with real coefficients. Let's look at this example. We have a fourth-degree polynomial function, and we want to completely factorize it. Now, we do know that it has a complex 0, which is -1 plus 2i. And if you look at this polynomial function, you can notice that all of its coefficients are real numbers. Therefore, if one of its zeros is -1 plus 2i, then the conjugate number -1 minus 2i must also be a 0 for this function. And these two zeros correspond to two linear factors, and we can try to find the product of these two linear factors to be x squared plus 2x plus 5, which is a quadratic factor with all real coefficients. With that knowledge, now we can use long division to try to find out the other factors. So we take the original function divided by its quadratic factor x squared plus 2x plus 5. Start the long division procedure. Don't forget, for long division, you do subtraction. and the remainder is 0. Again, this is what we wanted to see, which means that this original function equals to x squared plus 2x plus 5 multiplied by another quadratic factor, x squared minus 3x minus 4, which can be further factorized. Don't forget, if you have trouble factorizing this quadratic factor, use quadratic formula. And that is written now as the product of 4 linear factors. Again, the number of linear factors is 4, which correspond to the degree of this function. And that completes this problem.